Hello everyone and welcome. Today we're going to solve another dynamic programming example using SESV. Our example today is the best time to buy and sell stocks for max profit. This example falls into a few choices category and it's going to have 3 choices. To fully understand the problem, make sure that you have checked out the modern law of dynamic programming, also called SESV, in part 1 and 2. This tutorial is a part of the Data Structures and Algorithms class. Now step 0. We will get to know our problem and see if it's a DP problem. And a DP problem is a multi-stage decision-making process. Our problem is Leetcode number 174. We are given a series of numbers that represent the prices of the stock for each day. For example, the first day the stock price 1, the second day is priced at 2, and the third day the stock price at 8. Now we are allowed to buy and sell the stock with some constraints. The first one is we can only do one transaction in a day, and the second constraint is we must sell before buying a new stock. And for buying a stock, it doesn't cost anything, but for selling a stock, it's going to cost $2. Now the question is, what is the possible max profit that we can have with a given series of stock prices? Here we have 3 days, but the input can be much larger. If we look at our example right here, by human intuition, we can see that buying the stock at day 1 and selling the stock at day 3 is going to give us $5. 8 minus 1 is 7. We have $7 profit. And then we have to pay for the fee of $2 by selling the stock. So the max profits that we can have is $5. That is our example. Now is this problem a DP problem? And the answer is yes. We can have multiple decisions that are going to lead to multiple scenarios. And we are asked to pick the best scenario that's going to give the max profits. So trying different scenarios and pick the best one is a DP problem. Next, we're going to apply SESV step 1 to solve this DP problem by hand solving all scenarios. In other words, running its courses. We're going to start with day 1. When we are at day 1, we have 3 choices. The first one is we can choose to do nothing. We don't need to buy or sell any stock here. Our second choice is we can sell some stock. Our third choice is we can buy some stock. Now if we choose not to do anything, we can move on to day 2 and decide what we're going to do from there. So here we're going to have our day 2. Now when we're at day 2, we're going to have the same choices here. But we can choose not to do anything. We can choose to sell some stock, or we can choose to buy some stock. If we choose not to do anything here, meaning we're not going to do anything here, we're going to move to the next date. That is when we are here, day number 3. When we are at day number 3, we're going to have the same choices. We can choose not to do anything, we can choose to sell some stock, or we can choose to buy some stock. And if we follow the first choice of not doing anything, we're going to run out of days of stock to do. And when we run out of choices to do, that is one of our final states. We have completed a series of actions until we have no choice to make an action anymore. And for this series of actions, we chose not to do anything for all choices, and we have no profit or losses. And that is okay because cash in hand is also a good position. Now we're going to follow other choices. So if we are here at day 3 and we decide to sell the stock, we actually cannot sell the stock here because we don't have any stock in hand. So this is not a choice. And if we're here and we decide to buy some stock, we're going to buy it at a price of 8. And after buying this stock of price 8, we run out of choices to make. And we just bought some stock, so we have some stock. We're going to use the red dot here to indicate that we have stock. We buy the stock at $8. That's going to cost us minus 8. And we run out of choices to make. So this is one of our final states. Now we're going to continue all of these branches to have all our scenarios. When we are at day 2, when we're here, after making a first choice of doing nothing, we don't have any stock, so we cannot sell anything. So selling the stock here is actually not a choice. So we cannot sell the stock here. Another choice from this day is we can buy some stock. If we buy the stock here, our next state is where we're at day 3 and the stock price goes up after we buy it. When we are here, we had stocks. And because we just bought it, so our money is -2. Now from here, we have 3 choices. We can decide not to do anything. We can sell some stock, or we can buy some stock. If we decide not to do anything from here, we're gonna run out of choices to make. And that is one of our end states, where we still have a stock in hand, and our money is -$2. Now if we are here, day 3, and we decide to sell some stock, if we decide to sell some stock here, we're gonna make some profit, because the stock price has gone up from $2 to $8. So if we sell the stock, we're gonna have $8, minus the selling fee, that's gonna give us $6. Combine that with what we have in hand, which is -$2, gonna give us the profit of $4. And we also run out of choices to make after this day. So this is one of our end states. Now our last choice from here, can we buy a new stock? The answer is no, because one of the constraints is we must sell before we buy. So this is not possible here. With this scenario, this branch is done. And we're gonna continue with these 2 branches. So when we're here at day 1, and we decide to sell the stock, we actually cannot sell the stock here because we don't have any stock in hand. So this is actually not an option here. So we cannot sell anything here. Next, we're gonna move on for this decision of this branch. By our tree that we have here, you can see that we have run all possible scenarios for our particular problem here by hand. And now we're gonna look for the information that the problem statement asks for, which is the max profits that we can have. And as you can see, we have $0 here, -8, -2, 4, -1, 5, -1, and -9. So $5 is the most that we can make after running all scenarios. And that is where we buy at the first day, we do nothing at the second day, and we sell for the last day. We have $5, which is the same result that we have with our intuition. And that is how we solve a DB problem by hand, by pen and paper. Next, we're gonna turn this entire solution into code. First, we're gonna have a wrapper function that's called buy and sell stock. Second, always name your recursive function depth of search to emphasize the importance of depth of search in DP. Next, how many recursive calls do we have? We have 3 choices. That means we're gonna have 3 depth of search recursive calls. Next, state parameters. What do we put in these depth of search recursive calls? As you can see at each state, we need to know the stock prices. So we can see one of the state parameter is the index of the stock prices array. I'm gonna call it I. We need an additional information that we need to know if we can buy or sell stocks. That means if we have stock in hands or not. That is the red dot that we have here. So the second state parameter has stock. Next, changing states. If we choose not to do anything, how do we change from this state to this state? Well, that's the next day of the stock. So obviously index is gonna increase. So first we're gonna have increase the index here. The second thing is we do nothing. So if we have the stock, we still have it. If we don't have the stock, then we don't have stock. That means nothing changed with our has stock parameter. So it's gonna stay the same. That's for the doing nothing option. Second option, selling the stock. If we don't have stock here, no red dot here, we cannot sell the stock. If we have a red dot here, we have an option to sell the stock. That's mean for our sell choice. If we have stocks, we can sell. If we sell a stock, what is the next day parameter? It's gonna be another day. So the stock price is gonna move to the next day. That is I is gonna be +1. And we just sold the stock. So we're not gonna have the stock in the next day anymore. So the next day, we don't have stock anymore. Next option, buying the stock. We can only buy the stock if we don't have stock in hand. That means if we don't have the stock, we can buy. Then the next state is we're gonna have the stock. So the has stock flag is gonna be changed, and it's gonna be the next day. So we're gonna have I plus 1 here. And that's what we have for 3 choices. So we can see from here, at each state, we can either buy or sell. If we can buy, we cannot sell. And if we can sell, we cannot buy. So we can refactor this code a little bit better by combining 2 if logics to a single one. And the code looks a little bit cleaner. Now we're done with the choices. Next, final states is where we have no choices left. That is when we exhaust our array of prices here. That is when I equal to the prices length. We're gonna stop the branching. So we have the base cases and the branching. This code is actually done. We can print out the nodes, which is the prices of the stock, to compare it with our tree here. And we're gonna run our algorithm, starting at the first day and no stock. If we run it, we can compare the output of the console here with the tree that we have here to make sure our code is recreating our solution tree. Now the first step that we have is 1, 2, 8, and that's what we have here. The second step is 8, and that's what we have here. The next step is 2, 8, and that's what we have here. And the last step is 8, and that's what we have here. So by comparing the output with the nodes in the tree, we know that our code here has correctly recreated our solution tree. Next, SESV step 2. We're going to calculate the information asked by the problem statement, bottom up. The problem statement asks for the max possible profit. So when we hit an end case, we can just return here. And then when we are at the branching node, we're going to choose the max profits of 3 options. That means we're going to return 0 here. And we're going to get the return money of the do nothing option. And we put that into a variable. Then if we have stock, we're going to return the bigger value between doing nothing and selling the stock. Or if we don't have stock in hand, we're going to return the bigger value between doing nothing and buying the stock. So if we run it, it's going to return 5, which is the correct result that we want. Now our solution here has the complexity of 2 to the power of n, where n is the number of the stock prices. We're going to optimize this. Next, SESV step 3, we're going to cache distinct deficit calls to reduce the time complexity of our algorithm. What do we cache? If we look at our tree here, we can see that this subtree is repeated right here. That is where we're calling deficit with the state parameter of fails, we have no stock, and 2, index of the stock price. So we're calling DFS fail 2 here and DFS fail 2 here again. We can skip this by caching the return result here, and when we're seeing this call again, we can just look at the cache and return the result. Our cache key is all the state parameter combined, which is going to indicate this call, and our cache value is the return value of this call. So first, we're going to introduce a cache. Second, we're going to create a cache key. And if we look at the cache, we see it's not undefined, meaning we already have the result. We can just return it immediately. Otherwise, we calculate everything as normal, put the result into the cache, and then return the result. So if we run our solution, it's going to return 5, which is the same that we had before. But with the cache, the time complexity has improved into O of n, and that's a huge improvement. We can see how much time we can save by the cache by running the same input with a solution without the cache and a solution with the cache. So if we run it, they both have the same result, but the no cache solution takes 3.7 seconds. The cached solution takes only 1.8 milliseconds. We can also test our solution with Leetcode test cases. And you can see here, our solution passes all test cases and got accepted. Our quick summary. The characteristic of problem that can be solved by SESV. It is obviously dynamic programming problems. which is the multi-stage decision-making processes. The input characteristics, it can be any, it can be array, string, or graph. And our go-to solution to solve this kind of problem is SAMSDP. And the time complexity of the solution will always be the number of states created. If you find this tutorial useful, profoundly useful, then make sure to follow SESV tutorial, like, share, and subscribe to our channel, because dynamic programming is a mysterious subject with a lot of software engineers and algorithm learners. Until now, we have a solid way to solve DP problems. So if this is useful to you, let's help the world to demystify DP with SAMSDP by like, shares, and subscribe to our channel. It's gonna make YouTube algorithm to spread the video much faster. I also love to hear your story and how this course can help you to learn dynamic programming in particular or become a software engineer. So come say hi on LinkedIn. That is all for today's tutorial. Thank you for watching, and I will see you in the next video.